Block A slides across the frictionless tabletop and collides elastically with an identical Block B, which is initially at rest. After this collision, Block A is at rest and Block B continues along the surface and up a frictionless ramp to a height of 40 centimeters above the tabletop. If the two blocks had instead stuck together, how high would they travel up the ramp? So, we have two scenarios here. In the first collision, it's a perfectly elastic collision. That means the total kinetic energy is conserved before and after the collision. And Block A is moving with some kinetic energy and collides with Block B, which was initially at rest. And it goes up the ramp while Block A stops and Block B goes with some kinetic energy. You have to note that they have the same mass because they're identical blocks. So, in the second scenario, it's asking, in the first scenario, Block B goes up the ramp 40 centimeters. So in the second scenario, it's a perfectly inelastic collision where Block A collides with Block B and they stick together some kind of way and they go up the ramp. To what height is what they're asking. What height do they go up the ramp? So let me clean this up. So to teach how to solve this problem, I'm going to work backwards. I find this would probably be the best way for me to teach it. So, to start off with, for the second scenario, Block A and Block B stick together and they go up the ramp from height. The kinetic energy before they go up the ramp and the kinetic energy at the top of the ramp is going to be the same. The kinetic energy just right before they go up the ramp and the potential energy at the top is going to be the same. So we can write that as conservation of mechanical energy. That's half mv squared plus mgh is equal to half mv squared plus mgh. Okay. So these masses just cancel. Well, first of all, it starts off with some kinetic energy and no potential energy. This double block right here. And it ends up with zero kinetic energy and some potential energy. So these masses cancel. Let me clean this up a little bit. So we get half v squared is equal to gh. If we know the velocity, I'm going to call it the final velocity, and we know g, which is 9.8 meters per second squared about, we can solve for h. So let me save this, let me erase this and put it on the bottom. That's half v squared is equal to gh. We could, if we know the velocity, we know g, we could solve for h, which is the height that it goes above. Well, how do we solve for v? We know that the conservation of momentum before the two blocks in the second scenario go up the ramp is conserved. Whether the collision is elastic or inelastic, momentum is always conserved. So we can use that to solve for this final velocity right here. That's the velocity where the collision between Block A and Block B in the second scenario, where Block A collides with Block B and they stick together, that momentum is conserved. My fingers got in the way, I'm sorry. And to write that conservation of momentum, that is mv plus mv is equal to mv plus mv. So that's the momentum of Block A plus Block B initially is equal to the momentum of Block A and Block B final. So it starts off in the second scenario where Block B has zero momentum, so we can just erase that. And the blocks are identical and they have the same velocity because they stick together, so this is just going to be 2mv. So masses cancel and we get V is equal to 2V. So what do we have here? We find that the velocity initial, whenever two masses collide, whenever two identical masses collide in an inelastic collision, we have that the initial velocity is 2 times the final velocity. So whenever they collide, whenever the blocks after they collide go off with some velocity, they leave with half the velocity or initial velocity was. So that's every time the two blocks are identical and they collide with an inelastic collision. So this is initial and this is final. This is the final velocity we tried to solve for just a little while ago, which is right here. So we need to know this initial velocity. So let me save this equation. It's VI is equal to 2VF. And to solve for that velocity, let me erase all of this right here. We need to use conservation of mechanical energy again. So for the first scenario, we can solve using the conservation of mechanical energy. Let me write it all down. It's going to be half mv squared 1 plus mgh 1 plus half mv squared 2 plus mgh 2 is equal to half mv squared 1 plus mgh 1 plus half mv squared 2 plus mgh 2. It's a bit lengthy, but that's what it is. So in the first scenario, we know that block A has some kinetic energy but no potential energy. So we can erase this. And block B has 0 kinetic energy or potential energy, so we can erase this. And then in the final scenario, in the first scenario, in the final position, or after they collide, neither of the blocks have kinetic energy, and block B has the potential energy, but block A doesn't. So we just have here half mv squared 1 is equal to mgh 2. So here, it's better 2 than that. We know the masses cancel, and we know G and H. So if we know this velocity here, we can use this velocity. Remember, the block in the first scenario and the second scenario, block A had the same velocity regardless, which is this velocity right here and this velocity right here, which I've said that earlier near the beginning of the video. So we can solve for V here, V initial, to equal about, it's going to be exactly 2.8 meters per second. So now that we have this initial velocity, we can plug it into right here to get this final velocity, which is going to be VF is equal to 1.4 meters per second. And we can plug this in to this right here to get H, the height that the two blocks stuck together go up to. And we get H is equal to 0.1 or 1/10 of a meter or 10 centimeters. And that is the answer. And my book doesn't work this problem out, but I do. But it gives the answer in the back. So this is chapter 7, energy, number 19. Let me go to the back. Chapter 7, number 19, 10 centimeters. And you have to trust me that I worked this out right, because I thought about it a good bit. And the name of this book is Physics, a Conceptual Worldview with Problem-Solving Guide, chapters 1 to 13, by Kirkpatrick and Francis. Got this from my college. It's a pretty good book. I read the whole thing almost about 2 or 3 times. And it's a good book. And as far as this problem goes, that's it. See you later.